Welcome. Firstly, our team wanted to thank you all for your time and consideration for working with us through this difficult time, and we hope that you enjoy our presentation. We look forward to hearing from you in the future. Without further ado, let's get started. As you can see above, our project consisted of the design from the ground up of a two-story structure with parking, hydrology, traffic, and site design, all on an undeveloped lot in the east end of Louisville. There were a few design challenges which were of significant consideration, mainly including our client requested a green roof design, which we suggested as we thought that it was a very good idea. Secondly, the FEMA floodplain consumed most of our site, which became an interesting design challenge, mainly for selecting where the building will go. And the last thing that we would like to note is the COVID-19 pandemic, which has thrown us for a loop, to say the least, and has made the remainder of the semester very interesting. The breakdown of discussion topics for this presentation will include site design by me, Connor Jackson, hydrologic design by Sarah Haynes, steel structure design by Jacob Hubbard, foundation design by Jude Hutchins, budget analysis by Drake Jesse, and project scheduling by Amanda Greenwell. As we dive into the existing site conditions of this site, we need to look at the zoning, what the FEMA regulations are, and what the district regulations are of the site. In general, as you can see above me, we have an M2, M3 classification, which is a suburban workplace as according to logic. So when we looked at this information, we determined that there is a much lower regulation standard at this site compared to normal areas surrounding, because it is more out of the way and is secluded from residential areas. Moving forward, let's look at karst as the next existing site condition. Karst is a topographic feature characterized by sinking streams, sinkholes, and caves. We're familiar with this across the state of Kentucky, as I'm sure we all remember from the Corvette Museum, and we certainly do not want that happening to our site. So to negate this possibility of it happening on our site, we recommend a more in-depth geotechnical exploration as it would normally be recommended, because we want to minimize the possibility of a sinkhole arising out of surprise and thus costing a substantial amount on our client. The last thing we need to look at is FEMA. FEMA is the regulatory agency which lays out all floodplains and perennial streams that are protected. Our protected stream is Chenoweth Run, in which case we cannot build within 100 feet of this stream. The floodplain is also covering most of the site, as you can see in the diagram. This means that we have a very limited amount of space that we can use that is completely out of the floodplain, so small in fact that we cannot build out of the floodplain entirely. Thus, we had to do a little bit of grading, and we found a place that we could do the minimal amount of grading and still have a structure that is out of the floodplain. This was achieved, and we see as this location as the most feasible location for the building. Now, looking into general site design, we decided to follow a philosophy of flowing with the land. This allowed us to design for less grading, which means less work, which means saving money. Also, it gives a more natural feel to the entire site. As we have this natural feel, we recognize that it is very appealing to more high-end businesses because it is more of the green infrastructure type wave that we see in most modern construction. In addition, we see it as memorable and unique for the customers and guests and the clients that visit this business, meaning that your image will allow the businesses which rent out your business building to be more impactful on the people who visit them. Thus, you may generate more business and better business for your site. Now, looking into parking design, we decided to make a more unique flow in our parking lots rather than just a cookie-cutter large parking lot that you would find, say, at Walmart, Kroger, or the like. So looking at this video, we see that we have our main entrance, our side entrance, and our front parking lot, our dumpster pad, which is out of the way from all parking. We have our side lot, which is to be the one that's mainly used, especially for visitors, sidewalks, note, that are parking them all, and access to the rear parking lot and the rear access, which will be used mainly for people who are working in the building.
Hi, my name is Sarah Haynes, and I will be going over the stormwater design and the sanitary flow design for the site. For the stormwater, we looked at the peak runoff quantities that we would be able to see on the site. The table shown above is a summary of the calculations. So looking at those calculations, we looked at both the pre and post development for the site with the curve numbers and using the rational method. We use recommendations provided by Louisville's Metropolitan Sewers District's Design Manual. And we looked at the requirements for stormwater design and we calculated the peak runoff quantities for a 2-year, a 10-year, and a 100-year event. And all of them were under a 24-hour duration as recommended by MSD. The site is located in a floodplain and it's designated by FEMA as being in a zone A. And a zone A is considered a high risk area by FEMA, and it's described by having a 1% annual chance of flooding in the area. And so, as directed by MSD, we use a 1-to-1 ratio for the floodplain compensation when doing the stormwater design. So, our team has decided, in order to deal with the stormwater created from the post development and try and get it back to a pre-development or even under a pre-development condition, we decided to design for a detention pond on site. And our detention pond was calculated to be about a volume of 53,000 cubic feet. And that is quite large, but it also includes the floodplain compensation from the floodplain. And we decided that the detention pond would be best placed between the two parking lots on site. And we believe that overall a detention pond would be the best way to deal with any issues for the water in the runoff on site. So for our team and the sanitary sewer design on the site, we went back and referenced MSD's design manual, and we are proposing that the sewer line will connect from the building to the existing sewer line on site, as you can see on the side. And our team calculated that we would need a 6-inch pipe, and it would be about 220 feet long in order to connect it to the existing sanitary sewer on the site.
Hello, my name is Jacob Hubbard, and I will be doing the structural frame part of our proposal. Frame dimensions and beam choices. We were given dimensions as 120 by 200. We chose 30K 7 joists, W2150 floor beams, W3108 girders, and W831 columns. And there was 5 different scenarios for our columns to be loaded, different trib area and different factors that made the total load go up and down depending on the column. And the ones that were closest to needing upsize were these center columns because they have the max trib area and are right in the middle of the building, so they hold the most load, and that'll be important in the next slide. Green roof design changes. So our design challenge was a green roof, which pretty much only affected the structural side of the design. Green roofs are good environmental additions, but structural prices go up, and the reason for that is weight will increase because you're adding soil, trees, and stuff on the top, so weight is normally directly linked to cost. And with the increased weight, sometimes beams would need upsized if you were very close to needing upsize, but the only one in our case that needed it was that central column that I talked about, which will need to upsize to W1045 because it was already so close to needing an upsize before we added the green roof. That little bit that it added actually caused it to need upsize. So green roof benefits versus hindrance. Green roof benefits are increased aesthetics of the building. From the top view, flying over just looks better, and sometimes you can tell from the ground that it looks how it looks. And if you're in the building, you can go up to the green roof and see it for yourself. It's like a little park on your building. Decrease carbon footprint of buildings. So even though office buildings don't have the biggest carbon footprint, it's always good to decrease where you can, and that honestly just increases your almost curb appeal in a way. because you show you care about the environment and you're not just all about profit and you're willing to sacrifice money for, environmental benefit, then that just looks good on your company as a whole. And both of these can lead to increased business. So if you look like, you care about other things besides just your profit, and you invest in a green roof and your building looks good because it has a green roof, then that could attract potential customers. And the main hindrance of a green roof is the increased cost of installing and maintaining the roof. So you'll have more weight, therefore more structural costs, and then just maintaining the green roof once it's in. So both alternatives, one can generate more long-term revenue, and then one costs more in the beginning. So it really depends on how you want. Do you want to save money now, or do you want to make potentially more money in the future with the addition of a green roof? And that is our structural design part of the proposal. Thank you.
My name is Jude Hutchins, and my primary technical role was the foundation design. Using boring logs, soil data, and column loads from the structural system, a deep foundation and shallow foundation system were designed for this project to weigh the advantages and disadvantages of each. It was determined that the deep foundation would need 24-inch diameter piles with a maximum depth of 10 feet under each column. For the shallow foundation, it was calculated that 13 by 13 by 1.5 foot footings with 7 by 7 by 1.5 foot footings at the corners would be needed. These footings are large because their size had to be increased to meet the maximum settlement criteria of less than 3 inches. A footing sized at 13 by 13 by 1.5 feet is just not considered reasonable for a shallow foundation with our maximum column load of only 278.46 kips and an embedment of 2 feet. A smaller footing size could be designed by increasing the embedment because it would decrease the settlement. However, because rock is at depths of 1.3 feet to 9 feet, increasing the embedment would increase the likelihood of the footings encountering rock. Foundations are traditionally designed to be completely on rock or completely on soil to avoid issues with differential settlement. And since competent rock is at such shallow depths, a rock-bearing deep foundation is the more practical option. If you look at the drawing above me, you can see what we expect the deep foundation to look like underneath the building. Deep foundation systems are usually more expensive than shallow foundation systems, but in this case the deep foundation system is the better option economically because of the excessive amount of concrete that would be needed for the large footings of the shallow foundation. The deep foundation is estimated to cost around $92,000, while the shallow foundation is estimated at around $107,000.
Hi, my name is Drake Jesse, and I'll be discussing the budget for our project today. Preliminary calculations before beginning construction were as followed. Square footage was 120 feet by 200 feet for 2 floors. The median cost per square foot for the office building is $186, which we obtained from chart 501700. The Louisville location factor was 0.881 from the chart City Cost Index. The size factor for the building was 48,000 square feet divided by 10,000 square feet for a 4.8 size factor. Use 0.9 as the phi value. And the adjustment factor from 2008 value to 2020 is 103 over 100. So that makes your preliminary cost become 48,000 times 186 times 0.881 times 0.9 times 103 over 100 to give the grand total of a preliminary cost at $7,291,382. Then proceed to calculate the final numbers, final cost for the client. The structural design cost will be 1.2% of the preliminary cost, which comes out to $87,497. The site development and landscaping cost is going to be 3.5% of that preliminary cost, which comes out to $255,198. The overhead cost is then 1.54 multiplied by the structural design cost plus the site development cost, which comes out to $527,750, which then, when you add everything up, the total cost comes to being $8,161,827. And the proposed bid with profit comes out to be $8,978,010.
My name is Amanda Greenwald, and I will be discussing River City Engineering's approach to project scheduling. To the left of our slide, you will see the task list along with the duration and precedent set. To the right of the slide, you will see the graphic and flow chart that displays a sequential relationship between each task. It is important to note that the majority of our tasks occur within the first few months of 2021. This is when the majority of our design work will be completed, so our team members will have to devote a lot of time and resources during this period. The building location determination and trip generation are some of the first tasks on this list. That is because many future calculations and tasks depend on the knowledge gained from these two. Another task that is one of the first on the list is the steel design structure for the building. This is one of the first listed because it's a very involved process and one of the longer tasks in terms of the design process. Some of the types of tasks that can be pushed towards the end of the design process are the foundation systems report and the sewer design. And these were pushed back solely because they depend on previous calculations such as site explorations and grading plans to be completed. It is also important to note that the foundation construction starts at the beginning of the construction process that takes 18 months. This is so that it is complete and ready for the construction of the building and steel structure. It is important to recognize the dates that serve as milestones for the project's completion. Start to finish, this project is expected to take 26 months and 19 days, running roughly from the 1st of October of 2020 to the 19th of December in 2022. This includes everything from picking the site location all the way to the finish of construction. Another important milestone is the day that this project goes to bid on May 10th of 2021. This was important in our scheduling process because it is a 60-day bidding process. It also served as a large milestone because all of the design work up until this point had to be completed. Our group chose to leave a few weeks of leeway between the end of our design review and the start of the bidding process. That way, there was a buffer for any unforeseen circumstances that came up during the design process. The construction for this project is anticipated to take 18 months. For this reason, the project takes up to 26 months. This construction is anticipated to start on the 3rd of August in 2021. It is also important to note that River City Engineering will be providing 4 months of construction review over the portions of this project that we designed. Project scheduling plays an important role in getting the project done in a timely manner. This is crucial to getting the project done in the allotted budget. This is something that Drake will discuss further with the finances of this project.
In conclusion, this project has provided us with several new and difficult challenges, but we trust that our structural, hydrologic foundation, and site design will overcome these obstacles exceedingly. We hope that you all enjoyed our presentation, and we thank you for watching.